Ground conductor sizing in parallel systems isn't just about handling fault current until the breaker trips. There are multiple factors at play. Firstly, fault current limitation. Larger ground conductors offer a lower impedance path for fault currents. This limits the magnitude of the fault current. By limiting the magnitude of the fault current, it reduces potential equipment damage and arc flash hazards. Secondly, selective coordination. Proper ground sizing ensures the fault current will trip the circuit breaker upstream before any downstream overcurrent protective devices operate. This is critical for maintaining system stability and preventing cascading outages where a single fault triggers a chain reaction of breaker trips. Thirdly, equipment protection. Adequate ground conductors safeguard electrical equipment from overvoltages and insulation failures. These overvoltages and insulation failures can be caused by ground faults or even lightning strikes. Fourthly, grounding grid design. In larger facilities, particularly those with extensive grounding systems, using parallel ground conductors improves the overall effectiveness of the system. It reduces the grid impedance. This ensures proper grounding protection throughout the facility. Fifthly, compliance with standards. The National Electrical Code, known as the NEC, and other electrical codes, specify ground conductor sizing based on the circuit's current carrying capacity. This is in place to ensure electrical safety and system reliability as mandated by regulatory bodies. Regarding voltage reduction, it is true that increasing the number of parallel ground conductors can reduce the voltage at the fault point. However, it's important to understand that this doesn't automatically translate to a decrease in human voltage exposure. The human body's resistance remains relatively constant. The maximum fault current that can flow through a human, therefore, stays the same regardless of the ground conductor size. The primary safety benefit of using parallel ground conductors is in reducing the overall fault current magnitude and limiting potential damage to equipment. Let's consider the code requirement that when you run 2 runs parallel, the ground in each conduit has to be sized to the circuit breaker. For a 400 amps feed, one might use 3-500 NCM and 1 #3 ground, while for an 800 amps feed, you might need 2 sets of 3-500 NCM each with 1 #1/0 ground. The rationale behind this lies in ensuring sufficient capacity to handle fault currents and minimize impedance. Let's delve deeper into each of these reasons. Firstly, consider fault current limitation. When a fault occurs, a large current surge flows through the grounding path. The ground conductor must be adequately sized to handle this current without melting or vaporizing. If the ground conductor is too small, it could become a point of failure, potentially leading to more severe equipment damage or even fire. A larger ground conductor provides a lower impedance path, allowing the fault current to flow more easily back to the source. This limits the magnitude of the current and reduces the stress on the electrical system. Secondly, examine selective coordination. Selective coordination is a crucial aspect of electrical system design. It ensures that only the overcurrent protective device closest to the fault trips, minimizing disruption to the rest of the system. Proper ground sizing plays a vital role in achieving selective coordination. By ensuring that the ground conductor is large enough to carry the fault current, the upstream breaker will trip before any downstream devices. This prevents cascading outages and maintains the overall stability of the electrical system. Thirdly, consider equipment protection. Ground faults can cause significant damage to electrical equipment. Overvoltages and insulation failures are common consequences of ground faults, and lightning strikes can also induce damaging surges. Adequate ground conductors provide a path for these currents to flow safely to ground, protecting the equipment from damage. Fourthly, examine grounding grid design. In large facilities, a comprehensive grounding grid is essential for ensuring electrical safety. Parallel ground conductors are often used to improve the overall effectiveness of the grid. By providing multiple paths for fault currents to flow, the grid impedance is reduced. This ensures that all equipment is properly grounded and that fault currents are quickly and safely dissipated. Fifthly, understand compliance with standards. The NEC and other electrical codes set specific requirements for ground conductor sizing based on the circuit current capacity. These requirements are not arbitrary. They are based on extensive research and testing and are designed to ensure electrical safety and system reliability. Compliance with these standards is mandatory for all electrical installations. Let's consider the point about voltage reduction. While it's true that increasing the number of parallel ground conductors can reduce the voltage at the fault point, it's important to understand the limitations of this approach. The human body's resistance is relatively constant, typically around 1000 ohms. The maximum fault current that can flow through a human, therefore, is limited by this resistance. Even with multiple parallel ground conductors, the voltage at the fault point may still be high enough to cause a dangerous shock. The primary safety benefit of parallel ground conductors is in reducing the overall fault current magnitude and limiting equipment damage. It's also worth noting that ungrounded or resistance-grounded systems have different grounding requirements than grounded systems. In ungrounded systems, there is no intentional connection to ground. Ground faults can be difficult to detect, and the voltage to ground can rise to dangerous levels. Resistance-grounded systems use the resistor to limit the fault current to a safe level. This allows ground faults to be detected and cleared before they cause significant damage. In both ungrounded and resistance-grounded systems, the grounding requirements are designed to protect equipment and personnel from the hazards of ground faults. In summary, the rule requiring specific ground conductor sizing in parallel systems is based on multiple factors, including fault current limitation, selective coordination, equipment protection, grounding grid design, and compliance with standards. While increasing the number of parallel ground conductors can reduce the voltage at the fault point, the primary safety benefit is in reducing the overall fault current magnitude and limiting equipment damage. These requirements are essential for ensuring electrical safety and system reliability. Understanding these principles is crucial for anyone involved in the design, installation, or maintenance of electrical systems. The NEC provides detailed guidelines for ground conductor sizing based on the circuit current capacity. These guidelines take into account the various factors discussed above and are designed to ensure that the grounding system is adequate to handle fault currents and protect equipment and personnel. It's important to consult the NEC and other relevant standards when designing or installing electrical systems to ensure that the grounding system is properly sized and installed. Additionally, it's worth noting that the size of the ground conductor is not the only factor that affects the performance of the grounding system. The quality of the connections is also critical. Loose or corroded connections can significantly increase the impedance of the grounding path, reducing its effectiveness. It's important to use proper grounding techniques and materials to ensure that all connections are tight and corrosion resistant. Regular inspection and maintenance of the grounding system are also essential for ensuring its continued effectiveness. This includes checking the connections for tightness and corrosion, and testing the ground resistance to ensure that it is within acceptable limits. Any problems should be corrected promptly to maintain the integrity of the grounding system. The information presented here is intended for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer when designing or installing electrical systems.